Cold War flair. All right. My favorite examples of this, there's a whole bunch of these, is living a quantum life by meditating. You can make the universe provide for you, right? The secrets of manifesting. If you want things badly enough, you can make them appear, right? There's quantum selling secrets. The secret is if you put quantum in the name, it'll sell better. There's the laws of attraction. There's quantum mind power, right? All of these things are based on the idea that quantum mechanics is magic, that you can use this to bend the universe to your will. All right. All of this is crap, right? There are a lot of brilliant people out there who know a whole lot about quantum mechanics, and I promise you every single one of them is stuck writing research grants, right? Wanting funding really badly does not allow them, their knowledge of quantum mechanics does not allow them to make money magically appear. All right. Quantum mechanics may seem extremely weird, may seem almost magical, but at the end of the day, it's a scientific theory. It comes with the things that you get with a scientific theory. It comes with math, right? It comes with sort of rigorously defined physical processes and patterns of regularities in nature that you can calculate to astonishing precision. It is a rigorous and quantitative and well-tested theory of how the universe works. And it works really, really well. Right? This is a famous, slightly off-color XKCD cartoon. This curve here, right, is described by this formula. This is the very first quantum mechanical model ever constructed by Max Planck in 1900. It describes the wavelengths of light emitted by a hot object. Right? And this has been confirmed to astonishing precision. This slide right here is data showing that exact same curve, taken from the WMAP satellite, to measuring the temperature of the microwave background radiation in the universe. The red points are data, the blue line is the prediction of that formula, and they match perfectly. Right? This is an amazingly successful theory. And because it's such a successful theory, it enables us to do amazing things. Right? Because we understand about the wave nature of electrons, we know how electrons move through matter. And that allows us to modify materials to change the way the electrons move, which lets us make computer chips. We can make transistors inside blocks of silicon. We can pack billions of them together onto tiny little chips to power our computers and our smartphones. Right? Because we understand about the particle nature of light, that light is sometimes a wave, but sometimes behaves like a particle, we know how to make lasers. Right? And those lasers are used through fiber optics to make all the telecommunications connections that we rely on every day. Every time you use your smartphone, you're taking advantage of quantum mechanics twice over, through the computer chips and through the telecommunication lines that are powered by fiber optics. Right? Even something as obscure as tunneling has amazing applications. We can make a thing called a scanning tunneling microscope that uses this tunneling behavior to measure the properties of materials atom by atom, and even manipulate them. Right? We can push atoms around on surfaces to make patterns, to control matter at the atomic scale, because we understand exactly how quantum mechanics works. So some of the predictions of quantum mechanics may seem counterintuitive enough that they feel almost like magic. But ultimately, quantum mechanics is not magic. Right? It's science. And the key difference between science and magic, right, is the absence of lying. All right? So anybody out there who contacts you trying to pitch quantum mechanics as magic, right, is not on your side. Right? They're trying to take advantage of you. If what they're selling as something quantum seems too good to be true, it almost certainly is not true. And the person selling it is probably an evil squirrel. So I want to end basically on that cautionary note. Beware of the evil squirrels out there. I also want to offer a... How do we solve the Schrodinger? So there are lots of different answers to that, sort of. Right? So how do we solve Schrodinger's cat? The core assertion is that you really do get the results as if the objects are in two states at the same time. Now, there are different ways of approaching what happens inside the box. Right? The sort of orthodox language that most people tend to use is that the particle inside the box is both alive and dead at the same time. It's in the superposition, really in the superposition the whole time. There are theories though where ways of interpreting that give you it is really alive or it is really dead inside the box. You just don't know it. Those have some weird properties in other areas. So there are a lot of ways of approaching it. There's also the many worlds theory that says that your cat is both alive and dead inside the box, and after you open the box, the cat continues to be both alive and dead. It's just there's a version of you that knows the cat's alive, and there's a version of you that knows the cat is dead, and the universe sort of continues on in sort of two parallel tracks. All of these different variations of approaches to understanding what's going on inside the box, all of them give you exactly the same prediction of the results in the end. So on some level, basically every working physicist defaults to what David Merman called the shut up and calculate interpretation, which is you get the same answer no matter how you think about what's going on, and so most of us choose not to worry about it. But it's fun to think about those things sometimes. Questions?
You mentioned tunneling. The aspects of tunneling.
So the question is that I asserted that it takes 15 billion degrees to make fusion happen, but the temperature is lower for the sun thanks to tunneling. Is that true for everything? I believe I'm not an expert on the physics of nuclear weapons or fusion reactors, but my understanding is that in any of those contexts, you're probably relying on you're benefiting from that tunneling being there. So right there. So what's this have to do with quantum supercomputer? Are you thinking of D-Wave? So there's a company called D-Wave that has made a device that does a particular computation, and there's some controversy over whether it's actually quantum or not. Right? They claim that they use quantum mechanics to do a certain calculation faster than you could do with a classical computer. And quantum computing is a thing that's very real, and it turns on this business of things being in multiple states at the same time. Right? So a classical computer, you have bits in your computer that can be either 0 or 1, and each is definitely in one of those two states. A quantum computer can be in an arbitrary superposition of 0 and 1 at the same time, and that opens up a wide range of additional possibilities for computation. There's certain kinds of problems that you can solve faster using a computer that can do that than you can with one that just runs on classical bits. So quantum computing is a very big deal. There are a lot of people who work on that. It has some major applications, the most famous of which being you can use it to factor really large numbers if you can make a sufficiently large quantum computer. So lots of people are working on that. Most of those people think that what D-Wave has is an interesting curiosity, but not really a quantum computer. The conditions under which they operate the machine don't seem like there should be enough quantumness in the calculation for it to be doing something. But on the other hand, it seems to work pretty well. So there's this back and forth as to whether it's really quantum or not. I think the jury's still out on that. It's complicated by the fact that they're a commercial company, and so all of their hardware and algorithms and everything is proprietary, and so it's not very easy for people to study. But some people claim that you can write optimized code on a laptop that will do the same thing faster than the D-Wave thing does it. But there's a lot of arguing back and forth, and I don't think it's anywhere near settled yet. But when somebody eventually gets that to work, it'll be a very, very big deal. Yes?
How does this correspond to string theory?
So how does this relate to string theory? So string theory is an area of physics that's attempting to merge quantum physics that I talked about here with the other titanic theory of modern physics, which is general relativity. And general relativity deals with gravity warping space and time, right? And loosely speaking, works really well on very large scales if you're dealing with big, heavy things or things that are moving very fast. Whereas quantum mechanics deals mostly with very, very small things. Right? So those two work brilliantly in their respective realms. The problem is there are some places where they ought to come together, and they don't play nice mathematically. Mathematically, they're very different objects, and if you try to push them together using the tools that people have developed for other things, it just doesn't work. That you get nonsense out of the math. So string theory is an attempt to get around that by asserting that quantum objects behave like strings that vibrate in multiple dimensions. Right? And this is an area that mathematically has been very productive. People have put a lot of work into it. There's some really cool stuff that comes out of that, mostly relating to results around black holes and relating you can make a connection between the way certain kinds of black holes behave and the way some superconducting materials behave. There's an interesting physical connection there. Whether it's actually a theory that successfully marries general relativity and quantum mechanics is still an open question. Nobody's been able to sort that out yet. What it'll really take to sort that out is getting a good look at the few situations in the universe where you really need both of those things. And that's largely things like black holes, where you need quantum gravity if you want to understand a black hole. So a black hole is something that packs an enormous amount of mass. So it's a big thing that warps space-time. That's sort of the realm of general relativity, but it packs it into an infinitesimally small area, which is the regime of quantum mechanics. So you want to describe a black hole, you really need quantum gravity. We don't have that worked out yet. We don't have a really good look at a black hole yet. So that's coming. I don't know if people have heard the rumor. There's rumors. There's a press conference scheduled for Thursday by an experiment called LIGO. It's the Laser Interferometer Gravitational Wave Observatory. And they've scheduled a press conference for Thursday. They're trying to observe gravitational waves caused by things like two black holes spiraling together and combining into one. And people think that they may have detected such an event. And that sort of thing, that one event that they may be announcing on Thursday isn't going to solve the quantum gravity problem. But getting to see that sort of thing happen is the kind of thing that'll lead to useful information that we can use to test quantum gravity and see how that plays out. So it's an exciting period. Right? Nobody knows for sure what they're going to say at their press conference on Thursday, but whatever it is, it'll be pretty cool. So back there. Okay, so you're asking, so if electrons, we can't really say that an electron is orbiting in an atom like a little solar system, so how do we say that it's hitting a particular place on a screen, that sort of thing? It's a difference of scale. So it's true, we can't, if you tried to have an electron actually orbiting an atom like a little solar system at sort of ordinary energies, you can't really make that work because of the thing called the uncertainty principle, which says that if you know the position of something really, really well, then there's a big uncertainty in its velocity, right, and how fast it's moving. And if you try to put those together, you can't make an atom work like that. So what an electron in an atom really looks like is sort of a smeared out fuzzy cloud of probability around that atom. Right. So how do I go from that to saying that I detected this electron at this position at this time? The size of an atom is like an angstrom. It's like a tenth of a nanometer. All right. The size of the spot on that phosphor screen is like, a millimeter, right? And so the uncertainty in the position of the electron, that when we say the electron is right here at this time, there's actually enough uncertainty in that you're not actually doing anything all that. You're not really constraining it that tightly enough that uncertainty would mess you up. Right? So it's just the pixels on that camera are big enough that you spread the electrons out enough that it's not really invoking anything quantum. So, does that answer your question? So, other questions? Yes. So how did I end up doing this? So this is the strangest thing that ever happened to me in my life. So I really did talk with the dog, and I would do her half in that silly Andy Kaufman foreign guy voice that is in the video, because it makes my wife laugh, and I will do a lot to make my wife laugh. So inevitably, physics started creeping in, because it's what I think about a lot, and so physics jokes started appearing in those. And I was in a very strange mood one day, and I wrote a post for my weblog where I had a conversation with Emmy about the many worlds interpretation of quantum mechanics. And I wrote this up, and I posted it, and it got linked by the tech blog Boing Boing, and 50,000 people read that post that weekend. One of the people who read that post was an agent who contacted me and said, this would be a great idea for a book. And I said, huh? But I thought about it for a while, like, yeah, this is a really, good vehicle for talking about some weighty things, right? So the book has these, funny conversations with the dog about aspects of quantum physics and how she might try to use them to catch prey or finagle treats from me, and I explain how it really works. And then there's a longer explanation in each chapter of how the physics works out with occasional interjections from the dog when the going starts to get tough. And it turned out to work really, really well. So it was completely by accident. I easily, when I was a college student or a high school student, I could picture myself someday writing a book, but a book explaining physics with a talking dog was totally not anything I set out planning to write. But it's worked out pretty well. Well, the first one went well, so I did it a second time. So there's a relativity book as well. But the weirdest thing that ever happened to me. So yes.
What does quantum physics explain entanglement?
Yeah, entanglement. So the idea of entanglement is a big part of quantum physics. I didn't have time to. There's a whole bunch of stuff that I have time to talk about in this talk. Entanglement is this really powerful idea in quantum physics that says it's possible to make situations where you have a particle over here whose state is not determined, and another particle over here whose state is not determined. But the one thing you know is that when you measure them, they'll be exactly the same. Right? So if you measure this one, have it spin up, this one will also have it spin up. If you measure this one, have it spin down, this one will also have it spin down. If spin sideways, spin sideways. Right? They'll be perfectly correlated always. And that seems to violate relativity. Right? That seems to be a situation where you're doing something over here that affects what happens over here, but in a way that doesn't involve sending a signal from one to the other at the speed of light. Right? If you wanted to think of it in terms of signaling, you'd have to be sending your signal at speeds much, much greater than the speed of light. And that seems wrong. So physicists call this non-locality. Right? So it's violating the principle that something that happens here should only be able to affect things in its immediate local neighborhood until some time has passed. It's a really weird idea, and this is another thing. In the same time Schrodinger was doing his cat thought experiment, Einstein wrote a paper with two young colleagues where he introduced this idea of entanglement and said, this is an indication that quantum mechanics has to be incomplete. And nobody really knew what to do with that for about 30 years. But a guy named John Bell in the 60s showed that there's actually an experiment you can do that will distinguish between the quantum prediction that things are non-local and weird and the sort of theory that Einstein preferred. And people have done those experiments starting in the 1970s and continue to do them today. And every time anybody's done those experiments, it shows that the weird thing is true. That these things are really correlated in a way that does not respect the speed of light limit between the two. Lots of ways to think about how that happens, right? And one of the ways of reconciling that is to say that, well, all we really deal with is information, so it doesn't make any sense to talk about an underlying reality, and that's an approach that some people take. That's the sort of philosophical thing that bothered Einstein so much, but it really is a real phenomenon and something that people have to work very hard to understand. So,
what do you mean I really like?
There's a theory, a way of doing quantum mechanics is called Bohmian mechanics, or de Broglie-Bohm theory that does that sort of thing. It says that particles have definite positions and momenta at all times, but that they're pushed around by this guiding field that is sort of an extra wave that travels through the universe at speed, but that's a non-local thing. It changes faster than the speed of light. And that is an internally consistent way of doing quantum mechanics. It's kind of weird, but all of the ways that people come up with of doing quantum mechanics are kind of weird. So that's a thing you could do. So, other questions? Science fiction recommendations recently. People ask me this and then I go completely blank. Recent science, there's an astronomy book that I've been working my way through that's on a textbooky side of thing, but it's by Ethan Siegel, does a blog called Starts with a Bang, and it is like Beyond the Milky Way or something like that. But it's by Ethan Siegel from Starts with a Bang. That's a really nice survey of astronomy with absolutely no math in it, which is the best way to do astronomy. So last question in the back. So there are ways. So you're asking about I think the measurement problem or the sometimes observer effect, right? The notion that is implicit in the video that I started this with, where you open the box and that makes the cat inside pick either alive or dead, and so that the act of observing something changes its reality. That is one of the ways that people come up with to deal with the weird stuff, right? So the thing that's weird is not that you don't know what the state of the cat is while it's inside the box, because there's that sort of thing happens all the time, right? What's weird is the notion that when you open the box, you force it to pick one or the other, because we know that we only ever see live cats or dead cats. We don't see half-alive cats. Right? So one way of dealing with that is saying, well, the act of seeing it causes it to change, to pick just one or the other. And that's a whole class of theories that people do. There's another way of doing it, which is to say, which is many worlds, which is the cat is both alive and dead, and then when you open the box, the cat continues to be both alive and dead, but now you are in a superposition of knowing that the cat is alive and knowing that the cat is dead, and and the universe continues on with everything in a big superposition. And that also works perfectly well as a way of interpreting things. And so either of those, both of those, like I said earlier, both of those give you exactly the same predictions for measurements you can actually make. So it's sort of an aesthetic choice at some level, which way you prefer to think about the universe working. At least until somebody comes up with a way to distinguish. And I mentioned John Bell a little while ago talking about entanglement. There was this problem of, is this entanglement thing real, for like 30 years? Nobody knew what to do with it. And he sat down and thought really clearly and rigorously and analytically about what exactly does it mean for these two types of theories to be true, and then can we find a place where they predict different things? And so, and that worked brilliantly, and you can do an experiment that tests entanglement and show that it's really a thing. It's still an open question whether there's an experiment you can do that tests whether, observing something causes a physical change that makes it pick one state or the other, or whether the universe remains in an ever-expanding superposition. Somebody may come up with it someday. Nobody has yet.
So far,
absolutely. And the results that you predict work to 15 decimal places. So works spectacularly well. It's just how do you interpret what's going on inside the box? And that's kind of, at this point, is still essentially an aesthetic choice. You pick whichever one you like better. So I think we're out of time. I'm happy to answer questions down here. We'll have more questions. So thank you all for coming out. And
So today it gives me great pleasure to introduce today's speaker. He and I worked together for a number of years at Fermilab, and it's whoever decided to invite him, it's really a great pleasure for me to be here. He did his undergraduate studies at the Institute of Technology in Eindhoven. He got his doctorate from the University of Amsterdam in 1986 or so. He was then a postdoc at the State University of New York in Stony Brook before he was lured to Fermilab by Wilson Fellowship. He stayed at Fermilab for several years, and in 2010 moved to Argonne National Lab. During his career, in his doctorate, he worked on tau meson production and decay, and in P-bar-P physics on the D0 experiment, maybe most of you know, but maybe not, the kind of rite of passage for a Hadron Collider experiment is to do a good job of measuring the mass of the W boson, trying to do precision physics in a very high energy collider, and Marcel was instrumental in the first measurement that D0 made of that quantity in the early 90s. He then took on another thankless task as one of the leaders of the silicon detector project for the upgrade of D0. That was a device with 800,000 channels and nearly as many problems on the way to completion, but completion was achieved, and in fact it ran right through to the end of the collider running at Fermilab. So some rather impressive achievements in his career, but now he's paying for it. He's a member of the Bell 2 Program Advisory Committee. He's a member of the Large Hadron Collider Committee at CERN. He, for our benefit, is a member of the Electron Ion Collider Detector Advisory Committee at Brookhaven. And then to complete all this, he's got the pleasure of being a member of the Particle Physics Project Prioritization Panel, which is trying to give a shape to particle physics in this country this year. So it's with great pleasure. Please join me in welcoming Marcel D'Amato.
All right, well, thank you, Ron, for this nice introduction. I don't think that measuring the W mass is still a rite of passage for hadron collider experiments, because I don't think Atlas and CMS will be able to accomplish that measurement anytime soon. Anyhow, so again, thank you very much for having me here. Of these technologies. And to give you a little bit of the background, this actually came about very tangentially to the process that the particle physics community is going through at the moment with its prioritization, in the sense that Jim Siegrist, who is director of the Office of High Energy Physics in the Office of Science, would like to understand better, what the relation is of high energy physics to other science disciplines and society in general, and that's how this came about. And again, so this is somewhere, where it is still work in progress to understand these connections and the relationships. So if you have any feedback on that later, that would also be greatly appreciated. So you all know what particle physics does. Particle physics has its humble beginnings in a handheld cyclotron that was developed by Ernest Lawrence, and then it developed these very massive machines that have accomplished a lot. So the last machine that we had that had the energy frontier was the Tevatron at Fermilab, which has now been superseded by the LHC at CERN. Now, what particle physics does is it just studies the fundamental interactions of nature. It studies the fundamental constituents of nature and their interactions, which is nicely captured in this graphic. Now, the way particle physics goes at that is by building detectors, as anyone does. And the detectors that particle physics has built are really, I think, triumphs in instrumentation. The size of these experiments and the complexity of these experiments are really unique, I think, in the field of science. So here